Welcome to my first lab where I'll be exploring an object moving at a constant velocity. Today, our focus of study will be an object moving in one direction at a constant velocity. In this experiment, the object will be a golf ball being rolled along the positive x-axis. This is important to be able to understand and predict the motion of this ball through utilizing Newton's first and second laws. Newton's first law of motion states that an object will remain at rest or in uniform motion unless acted upon by an external force. This law explains that the ball is moving at constant velocity because no net forces are acting on the ball to change its velocity as it moves. Later in this lab, we will confirm that our ball has a net force of 0 by using the relationship between position and time, where the linear line formed is the constant velocity and represents 0 net force. Newton's second law is a relationship where force is equal to the product of mass and acceleration. As seen in the formula and acceleration time graph, when acceleration equals 0, velocity is constant. Later in this lab, we will utilize this relationship to predict the ball's future velocity and position in our simulated model. Here's the video of my golf ball where the ball is the system and the ground, air, and the rest of the room are the surroundings. The ball appears to be moving at what seems to be a constant rate because the frames chosen start after the initial push and end before the ball begins slowing down. I chose the frames without changing velocity so that Newton's laws, which state there should be no net forces applied. Tracker was used to analyze the movement of the ball in the video. The ball was used as a reference for the future frames, and the coordinate system was set so the origin was at the center of the ball in the initial frame. In this coordinate system, the ball moves along the positive x-axis. The axis could have been flipped so that the ball was moving in the negative x direction. Doing so would change the sign of the velocity vector to negative because the displacement is in the negative x direction over time. This would cause the slope on the position time graph to be negative. However, this change wouldn't affect the magnitude of velocity, also known as the speed of the ball. As you can see from the plotted data points, the slope is approximately linear, which correlates to a fairly constant velocity. Imperfections in the consistency of the slope will be explained shortly. To create the simulated model, the initial position was taken from Tracker to calculate the average velocity. The initial velocity was calculated using Newton's second law, where the net force was a zero vector, showing that as a result, the velocity stayed the same because the final velocity equaled the initial velocity. With these calculations, I was able to code to calculate the predictive movement of the ball and to display this prediction on a graph. Notable changes made to the code included changing the initial position and velocity vectors to the data found in Tracker. The data is in the x position because the ball is moving along the x-axis. A while loop was used to update the position of the object in small time steps. The while loop continues running until the very last frame of video, as seen by the time being set to 0.635 seconds, which is the time at the end of the video. The net force vector is set equal to 0. This was done because, as explained by a constant velocity, there is no outside forces acting on the ball. The velocity of the ball is predicted using Newton's second law in the equation. The mass of a standard golf ball was also inputted in kilograms. However, when conceptually understanding this lab, it's important to note that the value for the mass is negligible because the quotient of mass and net force in the velocity equation will always be 0 due to a net force of 0. Thus, the value for mass will not affect this. The position of the ball is updated using the new calculated velocity using the equation new position is equal to previous position plus the product of new velocity times the change in time. With these changes, the correct computer model is created. This model was used to examine Newton's laws because it shows a system that is moving at perfectly constant velocity. Here is the graph comparing the slope of the computer model and the slope of the actual data from Tracker, where the slope on the position time graph is the velocity of the ball is explained by the relationship velocity equals change in position over change in time. As you can see, although the lines are fairly similar, there are slight differences, notably at the end. This difference could be a result of forces like friction acting on the golf ball towards the end, accounting for the deceleration. As represented by the lines of best fit, the difference in the slopes of the lines is only 0.043. Because the lines are so similar, we can say that our object appears to be moving at a constant velocity. In the future, this experiment can be improved by completing more trials with a viewing frame that excludes all the parts where the ball isn't moving at constant velocity. The use of our simulated model was based on the fact that the net force, that is, the total number of pushes and pulls, equaled 0. Although we know that net force was equal to 0 based on the constant velocity, we can't be sure exactly how many forces are acting. However, as long as we know that the net force is equal to 0, we can say that the ball is moving at constant velocity as predicted by Newton's laws. In conclusion, this experiment showed that an object with a net force of 0 will move at a constant velocity, meaning no acceleration or deceleration. The object is able to continue moving because it keeps the momentum after the initial force has left. This was modeled in our simulated model. Slight differences in our observed model show that the small forces affect an object's motion. After looking at both a theoretical model and real-life observation, I hope you have learned as much about an object's movement as constant velocity as explained by Newton's laws. Thank you.